Well, good morning. No, good afternoon, grade 12s. Yeah, listen, I wanted to finish off this unit for you, and and talk to you about review and maybe moving the test to Wednesday next week instead of Tuesday. So I know it's a long weekend this weekend, but if you have any questions or need help, feel free to ask. Yeah, today we're going to do the last lesson, which is all about moving charges, and it's pretty straightforward how it works. Okay, so I'm just going to say a couple of things, just a little notes here, summarizing what we've learned so far. Okay, one, that charges are multiples of the elementary charge. That's what we learned in the last lesson, where E is 1.602 times 10 to the negative 19 coulombs. Yeah, so that's number one. Number two, what else have we learned? We have learned that energy equals Q times voltage. Okay, so that's the relationship between energy and voltage. Okay, number three, we have learned in the past that kinetic energy is equal to 1/2 mv squared, and that comes up often. Okay, and so basically these are the little tools that you'll be using. Okay, well, number four, actually I'll write one more, that the electric potential energy is K Q1 Q2 over R. Okay, so little things like that, these things will come in handy. This is like for charges that are far apart at first, or they're close together at first and they go very far apart. In other words, when R2 approaches infinity, right, we end up getting that equation right there. So those are the four sort of tools that you'll be needing to do this homework. Okay, it's actually pretty easy. Okay, I'll give you some examples. Okay, method. Okay, the general method is to do this. Okay, is to say that the kinetic energy, the change in kinetic energy is equal to the change in electric potential energy in the system. Now, sometimes, if you're given the voltage, so this, you use this if there's no voltage given, but you could also use the voltage if the voltage is given. Makes it really easy. That's if you have voltage. And remember, the word for voltage is potential. I'm just going to write it up here, is voltage, or just the word by itself. It's dumb. I'm getting a replacement pen soon. Just this word potential. Okay, that's what, if they say the potential, they mean voltage. Okay, if they say potential energy, they mean energy, but if they say potential just by itself, means voltage. Okay, all right, so basically that's the lesson right there. I mean, in a nutshell, that's it. That's all you have to do. Okay, so you're going to use the equation for kinetic energy, of course. Okay, so you can do that, but that's basically it. Okay, now I'm going to give you a couple of examples. We're going to start with point charges. Point charges are like electrons, protons, so on, alpha particles. Okay, all right, so let's do this example. Let's say you have two alpha particles. Now, if you don't remember what an alpha particle is, alpha particles are the nucleus of a helium atom. Okay, so there's two protons, two neutrons, and they have a positive charge. Okay, so they're both positively charged. And I'm just going to do this as like our first example, and I think I have the alpha particle charge right here. Okay, so here's the alpha particle charge, pardon me, and there's its mass. All right, so let's say you have two alpha particles. They're sitting in the nucleus of an unstable large atom, okay? And the distance between them is pretty close. Let's just say it's like 1 times 10 to the negative 16 meters, okay? That's R, that's the distance between them. Okay, and at first they're at rest, so their velocities equal 0 initially. Okay, so they're at rest. Now that's not voltage, it's velocity, okay? If it's voltage, I'll put the little hat on it, so like the little hat that I put right here on voltage, okay, in the equation. All right, so look, you've got these alpha particles that are separated by a very close distance. Let's say they're really close together, almost like inside the nucleus kind of distance. And then what's going to happen is they are going to fly out of the nucleus, because that's what alpha particles do. Okay, so they're going to separate. Okay, so now they're free to move, and they're going to separate because they repel each other, right? Now I'm just going to say, note, alpha particles. These alpha particles have the following statistics, and the numbers are in the table up here. That's why I included this table here. The charge, which we're going to need, the charge equals 2e, which is 2 times 1.602 times 10 to the negative 19 coulombs, right? And let's write down what that is right away. Okay, get my calculator. All right, so 2 times 1.602 exponent 19 negative equals 3.2, of course, 3.204 times 10 to the negative 19 coulombs, okay? Now, that's their charge, so they're both positive, right? And they're going to repel. Their mass is important too. Okay, so the mass is 6.65 times 10 to the negative 27, so I'm going to write it down. The mass equals 6.65 times 10 to the negative 27 kilograms. Did I get that right? Yeah. All right, so that is the charge and the mass on an alpha particle. Now, what's going to happen is these things are going to fly apart. And the question is, when they are a great distance apart, so when they are a great distance apart, what is their speed? Okay, this is kind of a typical question. Okay, so how fast will they be moving when they're a great distance apart? So what's going to happen is they start from rest, but this one's going to go that way, that one's going to go this way. Once they get really far apart, like several meters apart, let's just say, which is a great distance for these tiny little guys, then how fast would they be moving ultimately? Okay, so what is the ejection speed of these alpha particles? Okay, and the solution I'm going to write over here. The solution is basically, I'm sorry, my writing with this broken pen is terrible, but anyway, my solution goes like this, that the change in potential energy in the system will equal the change in kinetic energy in the system. Okay, now what is the potential energy in the system? Well, it's K, Q1, Q2 over R, okay, and that's going to equal 1/2 mv squared, but here's the deal, that's the kinetic energy of just one of these guys, but there's symmetry in the system, okay? This is like one of those conservation of momentum things, right? Because they have the same mass, they're going to have the same final velocity in opposite directions so that their total momentum is 0 all the time. So I'm just going to times that by 2. Okay, if they had different masses, we'd have to use conservation of momentum, and I'd have to give you one of their velocities ahead of time. Okay, then you would find the other one. All right, so anyway, there you go. There's this, this is the potential in the system, and there's 2 alpha particles. So I'm just going to write there are 2 particles both moving, and that's why we have to multiply the kinetic energy times 2. Okay. All right, so what are we doing here while we're solving for speed? They both have the same charge. So it's Q times Q equals 1/2. Well, this will cancel with that 1/2 over there. So let's just put mv squared. The only unknown, we know m, that's the mass of the alpha particle. We know what q is, that's the charge on the alpha particle. We know r, we know k. The only unknown is speed, so just solve it for speed. And really that's all there is to it. So it looks like a really sort of like modern physics kind of question, these particles flying out of the nucleus as radioactive decay. But you know, it's the solution is deceptively simple. So I'm going to put in these numbers here. 9 times 10 to the 9 times 3.204 exponent 19 negative squared. Divide that by 1 exponent 16 negative. Okay. Then I divide by the mass, which is 6.65 exponent 27 negative, like that. Then I have to take the square root. And I get 3.73 times 10 to the 7. 3.73, so let me, 3.73 times 10 to the 7, yes. So I get 3.73 times 10 to the 7 meters per second. Now that is about 10 times less than the speed of light. They can't go faster than the speed of light. If they have enough energy to go close, we have to use a different equation, one of Einstein's equations actually. If you get close to the speed of light, it's called the relativistic equation, but we'll talk about that later. Okay, it's not in this unit. But anyway, these guys are going pretty fast. Look at that. You know, like that is amazingly fast, about 1/10 of the speed of light. And these little guys with very little mass, they can really go. Okay, they can really get some speed in these problems. So don't be surprised by the large number. That's normal. Okay. So anyway, there you go. There's problem number 1. Okay, now I have another problem here I was going to show you as well if you have parallel plates. So anyway, long story short, for point charges, this is what you do, okay? You basically do it like this. Now let's look at my other example here. Now here we have a parallel plate apparatus, okay? Now it says here, a common technique used to accelerate electrons. So this is a basic particle accelerator, okay? You get electrons released from a hot filament from rest. The small hole in the positive plate allows some electrons to escape, providing a source of fast-moving electrons for the experiment. Now, this one's in your homework, so I'm not going to give you the final answer, but I'm just going to show you the steps, okay? Anyway, the magnitude of the potential difference, which is voltage, is 1200 volts, okay? The distance between the plates is 0.12 meters, so that's this distance here, DAB. Equals 0.12 meters. Now, it turns out we don't need that number, okay? Because they give us the voltage. As soon as you give us the voltage, you're making this question very easy, okay? So question A, electrons, here we see our electron is shooting out, okay? And there's a hole in the positive plate, okay? And it says, what speed does the electron pass through the hole? Well, the change in electric potential is equal to the change in kinetic energy. Well, this electron starts from rest, and so that's pretty straightforward. You end up getting Q times the voltage we're going to use here is equal to the kinetic energy that the electron exits with here with speed v, okay, as it exits. Now don't confuse the two v's, one's voltage, one's speed, okay? All right, now we just have to solve this. Notice that they don't give you the charge and the mass of the electron. Well, we need those numbers. You're going to get v squared equals 2qvab, like that, over m. So we do need the mass and charge. Good thing for you that I included these numbers up here. So these are electrons. Never put the negative sign. Don't put the negative sign in, but its charge is 1.602 times 10 to the negative 19. Okay, that's the charge on the electron, the elementary charge. And its mass is 9.11 times 10 to the negative 31. Now your book does the same thing. They don't give you these numbers, but they assume you can just, they're in the table in the back of the book. Just go ahead and look them up. They're also in the text. So anyway, you know these numbers. They are not unknown. Okay. So anyway, let's solve it for V. Okay, so I'm going to plug it in. I'll just say it as I'm doing it. I got 2 times 1.602 exponent 19 negative. Remember, no negative sign. Times 1200 volts divided by 9.11 times 10 to the negative 31 kilograms. And I get this big number. I got to take the square root, and I get 2.05 times 10 to the 7. So I get 2.05 times 10 to the 7 meters per second. Again, that seems like a very high speed. It is very high, but these guys are incredibly small. They can go really, really fast. Okay, and have this amazing acceleration because they're so light, right? All right, there's question A. Now, if you, I said I wouldn't do it for you. I did. I lied. Okay. Don't forget to take the square root, though, when you're doing these questions. Now, let's just look at some of these other questions. It says, is the electron pulled back to the plate once it passes through the hole? So, I mean, I think everyone can understand that a negative charge will be repelled from this plate, this negative plate at the bottom. Okay, it's going to be repelled there, pushed up, and then it's also going to be attracted to the positive plate. So you get two upward forces going to push that through the hole. Once it gets out, will it be pulled sort of back to this positive plate? The answer is no, because the field outside these plates equals 0. Their field is all tied up in between the plates. Okay, approximately 0, I should say. So there's no way they're going to pull it back. So basically, it's like kind of like if you get far enough away from the plates, it looks neutral, right? These positive and negative charges on the plates. So the answer is no. Okay. Now, in question C, it said, could it be modified to accelerate protons? Of course it could. If you want to modify it to accelerate protons, protons are positive charges. So what we would do is we would have to drill a hole in the negative plate, okay, like this. And then we have our proton. Here, I'll use a rainbow color. Here's our proton. And the proton could be fired through that hole, okay? So yeah, you could fire protons. In other words, the nucleus of a hydrogen atom. Okay, just strip its electron away, you've got a proton. And you could fire protons, okay, through the hole, okay? And then, of course, it'd be the same thing. Now it says find the speed of the emerging protons. Well, lucky for you, in question D, again, I have these numbers for you here. So the charge on a proton is the same as the electron. The mass of a proton is right here. Okay, so just use these numbers. Okay, that's it. Okay, so that's how you do these questions, guys. It's really easy. You just say that the kinetic energy will equal the change in electric potential, and you solve it for speed most of the time. Sometimes they give you the speed and you have to solve it for the potential or whatever. So but you're using, my point is, you're using equations like this all the time, okay? In fact, that one comes up all the time. All right, now, I wanted to leave you with, I will leave you to finish that question, first of all. But this one here is not from you have one like it in your homework, but I wanted to leave the one in your homework for you, okay? Because it's a difficult one, and I usually put it on a test. And this one's kind of an interesting question, okay? So let's look at it. It says an electron enters a parallel plate traveling at a very high rate of speed, 8 times 10 to the 7 meters per second. Okay, this is the voltage here across the plates is 600 volts, as they say. Okay, and then what's happening is it's fired across the plates, and it says what is the vertical deflection from the electron from its original path? So this electron, since the top plate is positive, as we can see from the positive wire that's attached to it right there, and this bottom plate here is negative, this electron will be attracted to the plate, and what's going to do is it's going to shoot out like that, okay? And what they're saying is, what is the vertical deflection? So the vertical deflection, I'm going to zoom in on this picture, I'm going to put delta dy, like this vertical, it's going to move up, okay, as it moves across. All right. Now, how do you do one like this? Well, I'm going to tell you that this is basically, because it's a uniform field between the plates, this is basically a projectile motion question. Now, if you've probably forgotten how to do projectile motion questions, so I'm here to remind you that when we do projectile motion questions, we break it down like this. Okay, horizontal, vertical, and launch. Does that ring a bell to you? Okay. Yeah, same thing here. This is basically, it's a uniform field, so it's like you throwing a ball across your room. Okay. Now the ball will not deflect upwards; it deflects downwards. But it's the same thing. You get it? Like it's like a uniform field in your room. So if you were to throw a ball horizontally, it will deflect downwards because of gravity, right? So here, this electron is going to deflect upwards because of the electric field. And you just got to handle it the same way. So look, Vx, they tell you, is 8 times 10 to the 7 meters per second. And this is a constant. It's not going to change, right? Because the force here is vertical. There's no horizontal forces acting on the object. V1y is 0 because it's moving horizontally at first, right? So that's your launch conditions. Now, for the vertical component, you're going to use the equation we always use, delta dy equals v1yt plus 1/2 at squared. Okay, that's the equation we always use. I'm going to say up is positive, the force is up, unlike gravity, which is always down. In this case, this force happens to be upwards in this question, right? So we're going to find out how much time it takes, and then we're going to use this equation. We need to find, we know this one is 0, so that one's 0, because the v1y is 0. We're trying to find this one, delta dy, so we'll need a and we'll need t. Now, if you remember from other projectile motion questions, the way we get time is by looking at the other component. So if we look at the horizontal component, delta dx will equal, t, we'll solve it for time, is equal to delta dx over vx. Okay, now that is a horizontal, just a uniform horizontal velocity equation. Now they do tell us what delta dx is. See this? The plates are 10 centimeters long. Okay, so those little parallel plates in there are 10 centimeters long, so it's 0.10 meters. I won't write meters. Okay, pardon me. This is 10 centimeters, so I have to convert it to meters, divided by 8 times 10 to the 7 meters per second. Now, that's going to be a really, like, look, when you're traveling that fast, like you're basically traveling at a very large fraction of the speed of light. It's going to travel through there in the blink of an eye, okay? So I get 1.25 times 10 to the negative 9, literally a nanosecond. 1 1/4 nanoseconds, 1.25 times 10 to the negative 9 seconds. All right, so we got our time. How do we find our acceleration? Well, this goes back to the lesson we did yesterday. To find A, okay, what we're going to do is the acceleration, we're going to use Newton's second law. So it's equal to the net force, which is the electric force, divided by m. So F equals ma, right? Now, what's the electric force? Well, in parallel plates, the electric force is Q VAB over DAB. Now, this was one of the equations we did the other day, okay? Now, that's the electric force. The mass is now new in that equation because, like, I'm dividing everything by the mass. And so this is from parallel plates, okay? And what you do is you plug these numbers into the equation and away you go. Okay, so it's going to be 1.602 exponent 19 negative times the voltage. The voltage is 600 volts divided by DAB is 2 centimeters. So that is this plate separation, DAB, not the vertical displacement, right? So DAB here is 0.02. So here, let me write down all the numbers divided by 0.02 equals, and then divided by negative. Okay. So what I did was I went 1.602 times 10 to the negative 19. That's our little electron going through there, right? Times 600 volts. Divided by 0.02, that's the separation of the plates, times 9.11 times 10 to the negative 31 kilograms. That's the mass of an electron, okay? Now, when I do that, I get 5.28 times 10 to the 15 meters per second squared. And I always get students who are like, that's too big. Well, you got to remember how small an electron is, right? So if you hit, let's say you take a tennis racket and you hit a ping pong ball, right? It's going to have a very large acceleration because its mass is so small. Now, if you take the same force and hit a medicine ball with it, well, then the medicine ball is not going to have very much acceleration because it has a very large mass compared to the ping pong ball. So acceleration is inversely proportional to mass. So the smaller the mass is, the larger the acceleration is. Well, these electrons, it's as small as you can get a mass to be. Okay, it's so small. So these very large accelerations, that is normal for electrons. Okay. All right. So now we're ready to answer our question. We've got the time and we've got A, right? So therefore, delta dy will equal 1/2 AT squared, okay, which is equal to 0.5 times the acceleration there times 1.25 exponent 9 negative squared. And I get 0.0041, 0.0041, so 0.0041 meters, which is equal to 4.1 millimeters. Okay, so yeah, just a few millimeters, it ends up going up there. It could, if it was going slowly enough, I guess, it could crash into that top plate, right? But it's going to miss it. And it's going to make it because like it would have to rise, if it started in the center of the plate, it would have to rise 1 centimeter. But it's still got another, 6 millimeters or so left. Okay, so there's your answer, and that's how you do a question like that. Okay, now let's do question B also. So we've done question A. Okay, the velocity. Now we've actually done all the hard work we need to do. This is question A. When we do question B, it's very quick. All right, so how fast is the electron shooting out of there? So it's going to be shooting out of here like this. What's that speed? Okay, now this is the one case where we're not going to use energy and kinetic energy and stuff. What we're going to do is we're going to do it with the projectile motion way. So we're going to recognize that when it shoots out, at the time it shoots out between the plates, it's going to have two components to its velocity, Vx. And I'm going to put in blue here the other component. This is V2y. V1y is 0. And in fact, there's this deflection angle too. That's one of the questions in the textbook is going to ask you about. Okay, so it's not in this question, but it's in your homework. They ask you what theta is. So this is how you find it. Okay, all right, so let's go ahead and find. We know what Vx is. Vx is constant. It's 8 times 10 to the 7 meters per second, never changes. Now V2y, we're going to use our motion equations. It's V1y plus AT. Now that one's 0. Okay, so we have A from the previous question, 5.28 times 10 to the 15. We have T from the previous question. Okay, so this is going to be 5.28 times 10 to the 15 times our 1.25 times 10 to the negative 9. See, I told you we did all the work for this. So now we just can use the numbers. So it's going to be that number times 1.25 exponent 9 negative equals. I get 6.59 times 10 to the 6 meters per second. All right, so that's V2y. Now that's not the answer. The answer is not what V2y is, it's what the hypotenuse of this right angled triangle is. Okay? So to find out what the hypotenuse would be, I'll use Pythagorean Theorem. So therefore I'll keep my rainbow color because I like it. Okay? V squared will equal Vx squared plus V2y squared, like that. Let's solve it. Okay? So I'm going to square my answer for the speed. I'm going to go plus 8 exponent 7 squared equals, take the square root. I get 8.03 times 10 to the 7 meters per second. And in case you're wondering what theta is, I know they don't ask us. This is the answer. But they don't ask us, but let's find it anyway. I'm just going to say note. The tan of theta will equal v2y over vx, and this is called the deflection angle. Okay, so that's the deflection angle. So let's just go ahead and we'll plug in our numbers. And by the way, this one is as hard as it gets for sure with the projectile motion thing. 6.59 exponent 6 divided by 8 times 10 to the 7. And then I take the inverse tan and I get 4.71 degrees. So I get theta equals 4.71 degrees. That's our deflection angle. If you like north of east, you know, whatever. And there you have it, ladies and gentlemen. That is your lesson on accelerated charges. So that brings us to course outline here. I'm just going to make a suggestion to you in the review at the end of the chapter. Like there's 10 homework problems here, but what I'm going to suggest, I'm going to put a practice test up. But I suggest that you go through the review and maybe look at some of those questions. You don't have to do them all. There's a review at the end of the chapter is what I mean. It's right after page 371. Don't do them all, but just test yourself with them. The answers are in the back of the book. See if you can do them, okay? I usually pick questions for the test from there, okay? And when I put a practice test, which I will do sometime today, you'll see what I mean, okay? All right, so I'm just going to tell you that the test resembles very much the homework as well. Okay, so that's it for moving charges, and that's it for this unit, guys, on electrostatics. Very short. Okay, you know, some odd questions like this in there, but I think, you know, if you just got to remember what the steps are, and I think you'll have no problem with it. All right, so enjoy your long weekend. Again, if you have any questions, I don't care if you ask me on the long weekend. All these days seem the same to me now. And unfortunately, Tuesday, if you want to think about something for Tuesday would have been the day we went to Canada's Wonderland. So there you go. It's the first time I haven't gone there on a school trip in like since before you were born. That's so weird thinking about it, but yeah, definitely since before you were born. I've been taking St. Matt's students there since like I was a child. So anyway, yeah, enjoy your weekend, guys, and we'll talk to you soon.